Howdy folks. So this is the fuselage of the RV-7A I've been working on, and I'm getting close to bonding on the canopy, and I thought this might be a good opportunity to make a short video to talk about some of the modifications that have gone into this canopy area. I'll go through them one at a time, and so that you can get an understanding in detail of what's going on. One of the first main modifications is that I am actually going to be bonding on the canopy. So I'm going to be using the Sikaflex 295 UV and the various primers and activator that are recommended on Sika's website. Now, as you may or may not know, for the Sika adhesive attachment of organic glass or polycarbonate or acrylic to a structure, they require a significant thickness for the adhesive itself. And for this size of installation, that bead thickness is about 1/8 of an inch. And so that resulted in some changes. So for example, these side rails right here, they had a joggle that was sufficient for the canopy thickness, but not sufficient for the canopy thickness plus 1/8 of an inch of sealant. And so I had to re-joggle these side rails. And of course, that turned them into a pretzel. Over here, this is kind of the tooling that I used in an arbor press. It's just some oak blocks cut at an angle. And I just re-joggled those a little bit at a time. There's a little bit of work needed with a shrinker to get them back into shape so that the curvature followed the fuselage correctly. And then they were twisted also, so it just took a lot of manual twisting to kind of get those things back into shape. Back here on the roll bar, this roll bar was trimmed down so that it is 1/8 of an inch narrower on each side than the plans would indicate, and also 1/8 of an inch shorter at the top. And the same is true for the non-movable portion of the roll bar. That is also narrower and shorter by 1/8 of an inch. So at the front of the canopy, I know it's common for folks who are using Sikaflex to use fiberglass for the attachment of the front edge of the canopy to the canopy skin here. I'm actually going to be using Sikaflex all around. And the rationale for that is that when a structural element like the canopy is attached to another piece of structure, and there ends up being like a large transition in stiffness, say from a fiberglass attachment to Sikaflex attachment, then it creates a stress riser right here on the canopy. And I've only heard of one Sikaflex canopy that developed a crack, and that crack was basically coinciding with the joint here. Now that could have been a function of the attachment of the side rail to the canopy frame with the little joint plates, but it also could potentially have been contributed to by a difference in attachment rigidity. So just to avoid that, I'm just going to be using Sikaflex all around. And as far as the concern of, well, Sikaflex is a flexible material, and so when it comes time to paint this fairing area, that paint is going to want to crack. I'm just going to add a flex additive to the paint at that location so that the paint itself will be flexible and not crack on that Sikaflexed area there. So another small modification I made was this joint plate here. This is the joint between the side rail and the canopy frame. And I added an extra rivet, I think at each of these locations, and I can't remember if there were 5 here per plant or not. But I added those extra rivets with the intent to just hopefully minimize any flexing that happens across this joint. So another modification that you may notice are this series of holes right here in the canopy skin. These are going to be for basically defogging vents for the canopy. There's not going to be any heat piped in from an engine muff or anything like that. It's ventilation only. And another RV builder building an RV-7 or 7A, I can't remember, is Mike from Caretaker Aero. He has a YouTube channel, and he was super kind. I contacted him to get some information relating to the measurement of where these holes should be located relative to the canopy. He was kind enough to look at a sketch that I sent, gave me a recommendation on the placement of these holes kind of in this direction. And so this is kind of the series of holes I added here. I also added just a few through holes. These are number 19 holes for number 8 screw. There's no nut plates below that. But in the event that I need to add some sort of vent or something like that to guide the air, to direct the air up onto the canopy, I've got those attachment points already put in. If I don't need that, they're just going to be there. On the underside of the canopy skin, of course, you can see the stiffening braces here. There's the middle one, and then of course the far one there. But I'm using this middle canopy brace as a plenum. So I've added a couple of cover plates on either side, and I also fabricated, it's going to be hard to see, but I fabricated a little rib for each side so that this volume is an enclosed volume. And then I found a fan on DigiKey. It's a little square 60 millimeter fan that is a nice fit for the size of the lightning hole. Added nut plates all around, and so that fan is just going to attach to that cover. For the back window, the attachment is also going to be Sikaflex, but that Sika is only going to be attached to the roll bar here at this location. Forward of the split line, I'm going to have Sika built up so that it will support the aft edge of the main portion, the movable portion of the canopy. But it's not actually going to be bonded from here to the canopy. It's, of course, only going to be bonded to the movable portion of the frame. The back edge of the rear window is not going to be attached with screws. Instead of that, what I'm going to do is I'm going to make a strip that's it just offsets the skin by the thickness of the canopy all the way around. And you can kind of see these two strips here. They are partially completed. Each of these little tabs will be joggled by the thickness of the canopy. And so the canopy itself will be trapped in between this flange here and the skin. So be trapped right in here. And that should eliminate any differential coefficient of thermal expansion issues back here at the back window. It should be free to move a little bit. And as far as sealing in there, I just plan to use that, I don't even know what it's called, but that kind of like tar type stuff that's used on, a lot of certified airplanes to seal the windows. So I'm just going to use some of that between the acrylic and the skin here. Now, up here at the front is where some of the more significant changes come in. There's a few different issues that either issues or maybe things that I just wasn't satisfied with about the design, as from the kit. And one of those is pretty common, I think. Basically, the forward fuselage skin curve right here didn't match the canopy skin curve. And so I ended up with what's common for a lot of folks is the little air scoops at 10 and 2, right around those curves. So I was unhappy with that. Additionally, this forward fuselage skin is supposed to be a butt joint with the canopy skin. And because the pivot point is in front of and below that joint, that butt joint, what happens is the forward, when you go to pivot the canopy up, this canopy edge, it doesn't just pivot straight up, it actually kind of comes forward and up during the first portion of the pivoting motion. And that means that, some folks, it's basically designed in, there's going to be a bind here. And the solution that Vance has is, you just bevel that back, create a gap in there, and, that eliminates the interference. So that's certainly one solution. Another concern that I had was the design of the subpanel is such that from one side all the way across to the other, there is not a continuous waterproof barrier. The subpanel is made in 3 pieces. There's this one in the middle, and then another curved bit on the other side. And I don't know, it just seemed unsatisfying to me that in the area where all the avionics are going to be going, that there were, potential gaps for water to get in. Not saying that, there's, all of these things are a matter of perspective, right? There are thousands of RVs flying with all of this stuff. So I'm not trying to say that there's anything wrong with Van's existing design. It's just, I wanted to do some things a little bit differently, and so I wanted to share the rationale for what that was. So I wanted a continuous strip between this gap here, or underneath the butt joint between the forward fuselage skin and the canopy skin. I wanted a continuous strip under there so it would be more waterproof. And then I also wanted a nice tight fit between these two skins. So all of that combined with the fit issue that I had here, basically it motivated me to kind of rework this whole area. And so what I did was I used Van's components as a guide, but I basically just refabricated all this stuff in here from scratch. Now, the reason for refabricating all of that stuff from scratch in combination with a bunch of additional work, which I'll show you, is to accomplish those things that I talked about. Good fit here, nice tight fit between the two skins, continuous water impermeable strip beneath the joint, no bevel at this location. And so I've added a mechanism. It's connected into the canopy handle. And by the way, I just don't have the latch installed right now. But it works like any canopy handle. You kind of push that in and unlatch and then relatch. But it's actually tied into a mechanism that goes up front. So the canopy handle, of course, normally it has a push rod that kind of runs back to this portion of Van's mechanism. That's all basically identical to what Van's designed. But I ran another push rod forward, and because of the location of the scat tube and the NACA duct and where the eye vent goes, it's kind of right about here, I did a bell crank to drop the push rod down so that the motion of this handle would be translated forward to a mechanism that sits up front. As far as the design of these push rods, that's a shorty, so that's no problem at all. This push rod here, I really don't know what the load is going to be on that thing. So what I did was I just, kind of ran the column buckling calculations on that push rod and on, this design push rod. And I made it so that the buckling load was similar between those two. This one's a longer push rod, so it's made out of fatter material. But, I had to start somewhere. That's where I chose to start. When it comes time for the Canopy latch handle to actuate this push rod, this bell crank, and then, the push rod going forward, these push rods, they don't actually engage this bell crank directly in line. Now that's not a good design approach, but it's what I chose. If I need to do something different, I can. But because these push rods are kind of coming in at a bit of an angle rather than directly in line with the push rod, the bell crank has a bit of a tendency to tip. And so what I did was I just added this UHMW wear plate right here, and I just polished off the heads of these bolts so that the bolts prevent, or this top bolt prevents the top end of the bell crank from pivoting that way. And then similarly down here, the bottom bolt prevents the bottom end of the bell crank from pivoting that way. And they're just tied into this, this structure here in I guess this is the F704 bulkhead. Now that push rod continues to come forward, and it connects up to this little bell crank here. Now there's a pivoting rod, a torsion rod here, and it goes almost all the way across. It ends at this series of two ribs, and it's supported here at this end. But the Canopy latch, it basically just actuates this torsion rod. And that in turn operates let me see if I can kind of hold this nice and steady for you. It operates a mechanism. It's a cam roller mechanism that moves this little plate up and down here. And that, the top of that plate is connected via a push rod up here to this lever. And the lever has a long arm back here at this end. It pivots around this fulcrum, and then that is where the canopy frame gooseneck arm attaches. So when I activate the latch, you can kind of see that this end is pulled down and this end goes up just a little bit. And what that results in is a canopy skin that just pops up and down just a little bit. It's about 1/8 of an inch. And that 1/8 of an inch there is sufficient to allow clearance at the joint between the canopy skin and the forward fuselage skin. Now the mechanism here that's operated by the torsion rod, it has two bearings. One bearing sits right here between these two bell crank arms, and similarly down here. And there's a cam profile and another cam profile. So basically, this mechanism turns through, I think it's about 60 degrees of motion. And for the first 30 degrees, this bottom bell crank is engaged in the cam slot. And then the cam slot widens out, and there's a bit of clearance here for this bottom bearing. But at the same time, this cam slot up here, which has clearance at this end, is engaging the tighter area of the cam slot. And so this top bearing is what guides this plate up and down at this end of travel. The top bearing is the tight fit in the cam slot, and then down at this end of travel, the bottom bearing is a tight fit in the cam slot. And something you might notice is right here, this cam slot has a kind of a little upturn. The similar arrangement exists down here. And the reason for that is I wanted these cams to go over center so that external forces would not drive backwards through this mechanism and either try to, like let's say I had the canopy up, so that's this location. I didn't want any kind of loading to try and drive this mechanism backwards so that it would come down, but when the canopy is actually up, like that would be bad. And then similarly, during flight operations, I want the mechanism to be in this position, and I wouldn't want air loads to try to bring the canopy skin to the popped up position. So both of these have, you know, a little over center feature here in the cam. And that's how I accomplished that. So with this pivoting lever mechanism, I decided that I wanted to really constrain and trap this well between the ribs. And if you've built one of these airplanes before, you know that, you know, on one side, Vans calls for a 1/8 inch thick UHMW. Basically, it's a glide bearing. And then on the other side, they've got, I think it might be around 5/8 of an inch thick, I'm not sure. And the inboard rib only comes back to about here. So I decided I really wanted to constrain it better than that. So I fabricated up both of these ribs. They're more or less mirror images of each other, with the exception that because, you know, the upper forward fuselage skin is kind of coming down at an angle, this flange and this flange are not quite at the same angle. And I've got you know, just a 1/8 of an inch spacer, kind of a guide, UHMW guide on either side of this. And that allows me to keep the span of the bolt going through here to a minimum. There's also, it's going to be really hard to see, but down below this heavy block on the movable portion, there's a hard stop. That hard stop is bolted in right here. And then similarly, there's a hard stop up front here, and that hard stop prevents this lever arm from coming down too far at the front. The back portion doesn't act as a hard stop at all, but what this one does, and then also this one does, is it offers really tight control of the distance between the two ribs, or actually between the two pieces of UHMW, and these stops are indeed trapped between the UHMW here and then also the UHMW here. So not having access to the loading information that Vans has, I really don't know what the loads are going to be on the mechanism and the hardware. And so in order to kind of bound that loading situation, what I did was I just took a look at Vans' design. And, you know, they use a 1/4 inch bolt up here at the gooseneck arm, and that bears on basically this rib. It kind of bears a little bit on the other rib too, but that rib's not well attached. When I say not well attached, I mean it's not rigidly attached all the way to the firewall. And so what I did was I just did a kind of back calculated what is the max load that that bolt could bear on the edge of the aluminum, either in the down or the up direction. And that gave me kind of a maximum load that joint would be able to handle. And then I just kind of made sure that the rest of the hardware was sufficiently sized, and also that the bearing load that my hardware sees is at a lower stress condition than what Vans has. And so that's one of the things that I did here was I added these doubler plates. These have to be super overkill, but it increased the thickness of the rib in this location from 25 thou to 75 thou. So this is a 50 thou thick doubler rib. Now, one of the things that's challenging about this modification, or was challenging about this modification, is that this curvature here, I had the air scoops at 10 and 2 o'clock, just like many other builders do. And I wanted to eliminate that. And so I made a new sub panel that goes all the way across. It's one continuous piece of material all the way across. That necessitated just fitting it in the longerons, necessitated a single piece be riveted in here. On the other side, on the passenger side, I was able to just notch the sub panel out, and it goes around the longeron. But in order to get it to fit into the airplane, this bit of material below the longeron had to be installed after the sub panel was in place. And so that's kind of why that's a separate piece. Again, I know I went totally overboard on the rivets, but the rivets don't cost hardly anything, and it was just a matter of putting in a little bit of time to do those. Now, to get the curvature right, of course, I need a riveting flange here. And to get that curvature right, I needed to form a flange. And so this is just a piece of 032 material that's bent at a right angle. And then I did shrinking kind of all along this edge here to create the curve. And see, there's one spot where I used a little fluting pliers to do a little bit more. That was kind of a fine-tune adjustment. But the amount of shrinking necessary to do this resulted in I couldn't use 2024 T3. I had to do the shrinking in O material. Basically, create this part in O and then heat treat it. And I thought about this, and I know I could send that part out to a heat treating shop. And but the problem is I only have a couple of these parts, and I'm not good at doing this kind of shrinking work, right? I'm a total noob when it comes to this. And so I just knew this was going to take, 3 or 4 iterations to get it to fit the way I wanted it to. And then when you consider that any heat treat shop is going to have a minimum lot charge for heat treating, it's probably going to be, I don't know, $150, $200, who knows what it is. But I'm going to be up against a minimum lot charge on every time I try to iterate through that. And then there's also another piece of knowledge that I have from, doing work in the engineering field, which is 2024, when you heat treat it, when you solution heat treat it, you heat it, bring it up to an elevated temperature, and you pull it out of the oven very quickly, quench it in water, and for like an hour, it's in a transient state called -W. So you end up with 2024-W immediately after quench. And that W is a transient state. Over the next 4 days, it'll harden up to the T4 condition. But during that, this hour or whatever you have to work, the material is really soft. It's just like dash O. And so if I needed to, it's common to get some warping during heat treating. If I needed to do some tweaking on this, I could, if I had the parts in dash W, I could do that tweaking while they're really soft. And then 4 days later, they'd be fully hardened up to the T4 condition. So for all of those reasons, I decided, I'm not gonna send these parts out to a heat treating shop. I'm going to do the heat treating here. But of course, that necessitated building a heat treat oven. So I ended up making this heat treat oven. It's tucked away in my garage under the shelf here. I'm not going to pull it all the way out. This video is not really about the heat treat oven, but I'll just kind of mention it here. I bought these refractory brick online. That was really the most expensive bit of the heat treat oven. The frame was constructed from an old bed frame that I got all the steel from an old bed frame that I pulled out of somebody's dumpster. And then, I made a control enclosure up front here that all that sheet metal, I just repurposed it. Somebody was giving away an old metal 2-drawer filing cabinet. So I just kind of repurposed all that sheet metal. Anyway, it's got just a super simple eBay PID controller on top here. And, it'll hold a set point. This thing, it runs on either 120 or 240 volt AC. Of course, with the 240, you get a lot more power. But I wanted it to be able to, I wanted to be able to do like heat treating of steel also. The temps for heat treating aluminum are really sub 1,000 degrees Fahrenheit. So it's pretty easy to get to those temps. But steels, you need to go a lot higher when you're going to be heat treating steel. So I did a test in the winter here in California. It doesn't really get that cold in the wintertime, but it was able to get up to 2,000 Fahrenheit. Of course, I don't need anywhere near that temperature for aluminum. But anyway, yeah, so I built the heat treat oven. It's long enough to be kind of a general purpose. If I ever want to build another airplane, I could, fit a wing rib in there. It's not very wide. It's only about 6 inches wide inside. But yeah, so that heat treat oven came in handy for heat treating those flanges that I had formed. Another area where that heat treat oven came in handy was in the heat treating of these doubler plates right here. So I used these ribs, they're 0.25, and so I had a 3/32 bend radius right here at this location. And so that meant the bend radius needed for the doubler plate was, pretty darn tight. And you can't do that in T3 material. And so I formed these flanges out of dash O and then heat treated them as well. And they warped a little bit after heat treat, but it only took a few minutes with the shrinker to take the warp out, and then they were a really nice fit. But you can kind of see they nest. Let's see if I can get a good view of that. Yeah, so they nest quite nicely with the flanges of the rib above. So with these arms that pivot around the fulcrum, which is kind of right here, this end goes up and down, and so it's not just a hole through there. There's actually a slot for that pin to fit through, and I really didn't want the pin to rotate, or certainly not very much when the canopy is lifted up and down. When I say lift it up, I mean you're actually opening the canopy or closing it when you're getting in or out of the airplane. So I didn't want the all of that, whatever it is, 45 degrees of canopy rotation to be occurring in these arms here,
because that would just, over time, that would just, kind of wear out the aluminum hull, and then you'd have to remake these parts and install new ones. I mean, I'm sure it would take a long time, but I didn't want to do that. So I really wanted to prevent that pin from rotating as much as I could. So I just kind of did a modification of Van's design. I used these 3/8 inch 4130 tube chromalloy tubes, and it's a nice tight fit on the flange of this. I forget what that kind of stud is. And then similarly over here. So that tube will not rotate, and it will not permit that pin to rotate, but it will permit the pin to kind of move, up and down in the slot. I hope that's clear. And then over here on this side, I wanted to have some kind of indication in the cockpit that, the canopy, this sort of pop-up mechanism is popped down when it comes time to push the throttle in. And so I added a couple of limit switches here. These are just micro switches, and they're like $5 a piece, maybe not even that, I don't know. And so they just sense both the presence and the position of those pivot pins. And I'll tell you what, I'll try and see if I can get a video of this while I'm actuating. So you can kind of hear the pins or the switches actuate when they're pressed in. And these mounting brackets, they're mounted on screws. Right now, the hole in this sub panel is just a number 19 hole. I try to be careful with the position of the brackets, but if I need to adjust the position of the switch at all, I'll just slot the hole in this panel, slot it up and down a little bit, and that'll give me some adjustment to adjust that switch up and down. Similar to up front, I went ahead and added a couple of micro switches back here at the Canopy latch rod, and they work like basically the same as other people have done, where it senses on the lug that extends down from the canopy, and so it just like up front, it senses both the presence and position of the canopy and the latch mechanism. Okay, kind of the last thing here that's pretty, I don't know if it's significant or not, but it's a change from what I've seen other builders doing, is with respect to the gas struts. So the gas struts attach here and extend up to that ball, and of course those gas struts, if I have a tight fit of the joint between these two skins, the gas struts are just going to make me regret that. And so what I decided to do was to add a way to react that force. Now, other folks, they'll put a adjustable stop up here. Certainly nothing wrong with that. Buried underneath that skin. Certainly nothing wrong with that. That accomplishes a similar approach. But what I chose to do was add a bracket here. This bracket, sits mostly right behind the panel, which mounts to these. And then that bracket's got a bearing on it. And so the gas strut, it pushes, on the stud, and that force is transmitted through the mounting point, which, as you can see, is not just a plain old rectangle, through the mounting point, and then this little wedge mechanism, and reacted through this bearing down into the structure. So it really just, accomplishes a similar thing to what the adjustable bolt is up front, but it short circuits the force, down right into the structure, rather than all that force being transmitted through the canopy frame and just kind of like distorting this whole portion of the canopy frame. And so I've done some measurements, and with the gas struts installed, with the gas struts not installed, I took measurements on like
how's my gap here between the forward skin and the canopy skin, and then kind of replicated that same test, but with the gas struts installed. And, there's only a few thou change. So it does a reasonably good job of reacting that force. So the last thing I thought I would show you is, just kind of how these gas strut bearing stop dealios work when the canopy is being raised or lowered into position. Right now, those you might notice these stop blocks here. They're not primed. The geometry is more or less correct, but I'll probably have a set machined out of steel. I don't know, maybe not. Maybe I'll stick with aluminum. Anyway, this is probably not the final version of them. The geometry will be the same, but it'll be a little bit cleaned up. These are maybe a bit on the crude side. So the canopy's unlatched right now. I'm going to just pivot this up, and so you can kind of watch what happens. So that stop plate kind of gradually engages the bearing, and then it just rolls down and reacts that force. So it accomplishes, more or less the same thing as that adjustable nut. It's just maybe a little shorter path to short circuit that gas strut force. All right, well, I hope you enjoyed seeing and hearing about some of the modifications on my RV-7A project. It's certainly taken a lot of time, but it's been fun along the way. I'm one of these people who enjoys the actual building experience and kind of figuring out all these different challenging ways of doing things. It's probably why my airplane's not finished yet. No, it's totally why my airplane's not finished yet. But that's okay. It's all right with me. And I just wanted to share in case anybody else thought they might find it interesting. Take care.